So let's look at a couple examples of how I can use my rules for combining capacitors in series and in parallel and use those for a couple simple examples for sets of capacitors. So for starters, I've got capacitors C1, C2, and C3 here, and let's be very clear. I'm letting them have capacitance values of 1 farad, 2 farads, and 3 farads, which are way too high for these to be realistic capacitance values. Right? So these should be either microfarads, nanofarads, picofarads. All those would be sort of appropriate capacitance values. I'm simply using 1, 2, and 3 farads just to make the math easier as I work through this. So for starters, what I want to notice is, again, I have two elements, C2 and C3 here, that are initially connected in parallel. So if I think about coming across, here's capacitor C1, and if I try to connect C1 to either of my other two elements, this junction here means that I've got two pathways that I can go down to try and connect with C1. And so part of what that says is that, well, I just need to connect C2 and C3 together first. They're connected in parallel. So the first thing I want to do is keep track of what that tells me. In this case, it tells me that the voltage drop across both those capacitors is going to be the same. So V2 equals V3, and that's going to be the same as the voltage drop across the equivalent capacitor when I combine the two of them here in a minute. So that's what V23 is. I also know how to calculate this. So if I have capacitors connected in parallel, then their equivalent capacitance is just the sum of the individual capacitances. So when I add together, I get that the capacitance of the equivalent capacitor 2,3 is nothing more than the capacitance of 2 plus the capacitance of 3. That's 2 plus 3, that's 5 farads. So I have replaced those two individual capacitors, C2 and C3, with an equivalent capacitance that happens to have a value of 5 farads. Well, now I'm left with two capacitors in my circuit, and it's reasonably easy to see that those two are connected in series. So there's a single pathway that you have to follow to go from capacitor 1 to capacitor 2, 3 on back out. These two capacitors are connected in series. The first thing I know is that means that the charge on them has to be the same. So the charge on capacitor 1 is the same as the charge on my equivalent capacitor 2, 3, and it's going to be the same as the charge that's on the equivalent capacitor 1, 2, 3 when I combine all three of them here at the end. Again, I know how to calculate what the equivalent capacitance is when I combine two capacitors in series. So the equation 1 over C123 equals 1 over C1 plus 1 over C23, that will let me calculate the equivalent capacitance. I'm going to rearrange it and use the version of this equation that's already solved for C123, the equivalent capacitance, just to minimize my mistakes. And so I want C1 times C23 over C1 plus C23, so that's 1 times 5 over 1 plus 5, and this is 5/6 of a farad. So when I combine all three of these capacitors into a single equivalent capacitor, it has a capacitance value of 5/6 of a farad. So there's my first example. Let's take another example. I've moved where C1 is. Instead of being before the junction, C1's now after the junction. And so that changes the order in which I need to combine things. So again, what I notice now is the first thing I need to do is recognize that C1 and C3 are connected in series. So there's a single pathway that connects them both. They're connected in series. Again, that means that the charge on these two capacitors has to be the same. So Q1 has to be the same as Q3, and that's going to be the same as the charge on the equivalent capacitor when I combine them here in a second. Again, I can calculate what the capacitance of that equivalent capacitor is when I combine them using my equation 1 over C13 equals 1 over C1 plus 1 over C3. I'm going to rearrange that, use the version that minimizes my algebra mistakes, and so that I get that the capacitance, the combined capacitor 1,3 is C1 times C3 over C1 plus C3. That's 1 times 3 over 1 plus 3. That's 3/4 of a farad. So I have replaced these two individual capacitors with a single equivalent capacitor that doesn't change anything else that's going on within my circuit. So now I have two capacitors, C2 and C13, and I see that they're connected in parallel. That means that the voltage drop across each of those capacitors has to be the same. So the voltage drop across C2 has got to be equal to the voltage drop across this combined capacitor, C13. That's also going to be equal to the voltage drop across 1, 2, 3 when I combine all three into a single element here at the end. I know how to calculate the equivalent capacitance for two capacitors connected in parallel. It's simply add up what those two values are. And so in this case, I get that C123 is C2 plus C13, that's 2 plus 3/4, that's 2.75 farads. So there's the calculation telling me that when I combine all three of these capacitors into a single element, the equivalent capacitance of that single element, C123, is 2.75 farads. So when we're working through these problems, you'll notice that basically what we've paid attention to is a couple things. First is what capacitors are connected in what way. So I need to start by recognizing which capacitors are connected and how are they connected. As we've seen, the order matters, right? We changed where C1 was, that changed the order in which things needed to be connected, that changed the final value at the end. The second detail that we probably want to pay attention to is, well, what does it mean? So when we connect something in series, it means that the charge is the same on that set of capacitors. When we connect capacitors in parallel, it means that the voltage is the same across those capacitors. And then lastly, what's the rule for combining the capacitors in this particular way? So we have a rule for combining capacitors connected in series that we need to use to calculate the equivalent capacitance of two capacitors connected that way. We have a different rule for calculating the capacitance of capacitors that are connected in parallel. So just make sure that we use the right rule and calculate the equivalent capacitance.